speaker. Today's speaker is McCullough from CERN. He received a PhD from Oxford University at 2011, and after that, he worked as a postdoc fellow at MIT and CERN until 2015. And after that, he experienced a job in CERN and Cambridge University. And from 2020, he has been in CERN again as a professor. So today he's going to talk about Gegenbauer Goldstones. So please start.
Yes, thank you very much. And I'm delighted to be able to give this talk. This is one of the benefits of our the virtual life we've discovered. It's brilliant to be able to do this. So today I'm going to talk about some recent-ish work with Gauthier and Ennio Salvioni. We've published 2 papers now. The last one was just second paper was just accepted. And we're probably going to publish 1 or 2 more papers. So this is a really fun project that I've really enjoyed. It actually came about when we were studying the Higgs self-coupling. Basically asked the question, how big can Higgs self-coupling modifications be in realistic theory models? And then this led us down a rabbit hole, and we sort of followed this question around, and then we discovered this whole structure that is completely independent of that question and very interesting. So I'm gonna this talk will sort of be in 3 parts. The first will be a sort of broader motivation, maybe for some of the senior people, it won't be very interesting. It's stuff you've heard a million times before, but I think it's useful, especially for junior people and PhD students, to understand the background. And I'm going to discuss the hierarchy problem in the way that I view it, which will help inform the rest of the talk. Then I'll discuss Gegenbauer Goldstones and how we might find out that the Higgs boson is a Gegenbauer Goldstone, and how this can address questions of fine-tuning in the Higgs sector. And then in the last part of the talk, I will discuss a recent model that we put out called Gegenbauer's twin. And please, I prefer to have questions during the talk. If you have any questions or comments, I have left room in the way I designed the talk that we can have comments during the talk, and it shouldn't take us over time or anything like that. So please shout out, and even if it's something basic, please ask, because if there's something that you haven't understood what I'm saying, then probably a lot of other people haven't, and so it'll be very helpful for all of us if you ask questions. Okay, so what's the backdrop here? The sort of the broader motivation. Well, I would view this from the sort of quasi-historical perspective that for every scalar that we have, scalar particle, scalar field that we've discovered in nature, until they have had properties that are calculable within some more fundamental theory. That more fundamental theory is, the microscopic theory, the UV completion. We have different terms for it. And there are 2 examples of this that I'll put here, but there are more. The first is for superconductors. Pairs of electrons form a condensate in a superconductor, and that condensate is essentially a scalar, and it has an excitation associated with it, which is a scalar field. And that's the Landau-Ginzburg scalar field in the Landau-Ginzburg model of superconductivity. Now, in that model, that scalar field has properties in particle physics language. We would call it the quartic interaction and the mass. In condensed matter languages, we use different words for the same thing. And those properties can be calculated within the more fundamental theory, which is the BCS theory of superconductivity. And that's the more microscopic UV completion. And so we can derive the sort of macroscopic properties of this phenomenological model from the microscopic theory, which is BCS theory of superconductivity. A second example concerns mesons. We'll just discuss pions, for instance, in QCD. If we had only built a collider that could get to, 1 GeV, then we would just have to work with the theory of pions and mesons and baryons. And the theory of pions has some parameters. Some parameters associated with symmetry breaking, but they're similarly a mass, a quartic, and so on. And within the chiral Lagrangian, which is the effective theory of pions, you can't derive those parameters from somewhere. They're just parameters that you measure by doing an experiment. However, in the UV completion, which is the more microscopic fundamental theory, we learned that those pions are actually a condensate of quarks. And all of the properties of the pions in the macroscopic theory can be calculated from the parameters of the microscopic theory. So for instance, once you have QCD and you have the quark masses and the QCD gauge coupling running, you can put that theory on a computer and actually calculate what the mass of the pions is. Now you can't calculate that parameter within the chiral Lagrangian, within the pion effective theory, but when you have the UV completion, you can calculate it. What about the Higgs then? That's obviously what I'm going to focus on. Well, the Higgs, we know that the standard model has a UV completion. There is a more microscopic theory. And the reason we know that is that unless I'm missing something, if I ask you this question, which is what does the standard model predict if you collide electrons at 10 to the 277 GeV? If you can't answer that question, then the standard model is an effective theory. It's a macroscopic theory that has some UV completion.
I have a question, little bit question.
Yes. Yes.
Where it from 10 to 277 GeV? Is that something like Landau pole?
Yes, exactly. Very good. Excellent. Yes. So I chose that. I chose that energy scale because sometimes people like to pretend gravity doesn't exist. And if they like to pretend gravity doesn't exist, then the Landau pole exists. So that's exactly where it comes from. I think I chose that a few orders of magnitude above the Landau pole just to make it very strongly coupled. Fantastic. Okay, so what about the Higgs? Now there are different logical possibilities. Of course, it's possible that maybe even within the UV completion, within the microscopic theory, whatever it happens to be, that we will not be able to calculate the macroscopic parameters, the Higgs mass, the Higgs quartic, and things like this. This is a logical possibility. There's no law of nature that says at each layer of reductionism, you have to be able to calculate from the new theory. So that's a logical possibility, but that's a very, very depressing possibility because if you take it to its logical conclusion, that means the end of reductionism, and it means that the end of explanatory power, and we should all just go and do something else. The other logical possibility is that will be calculable within that microscopic theory, and that fact alone can enable us to make educated guesses about what that microscopic theory will be. After all, that's exactly what happened with QCD. With QCD, with the pion Lagrangian, very, very smart people made educated guesses looking at the spectrum of baryons, the spectrum of mesons, the masses of pions, using Goldstones theorem and things like this. And they were able to guess, even before we had built colliders to go to high enough energies, they'd been able to guess at the structure of flavor symmetries, guess at the group structure of the gauge theory and the UV. All of this was essentially the same strategy, trying to guess, make educated guesses from the clues that are left within the IR theory by assuming that the parameters of the IR theory can be calculated from the parameters of the microscopic theory. And so there are two sort of branches to this. We want to make an educated guess because we want to figure out what that microscopic theory is. And the two ways to do this are to use experiments. We can use experiments and go to higher energies, or indirectly probe those higher energies by going to higher precision measurements. That's one branch. And the other branch is theory, using these clues and trying to make educated guesses, trying to write down models that might be the UV completion, and then look at their predictions and compare that to experiment. Both of these strategies are important. I wouldn't say that one of them is necessarily more important than the other one. However, to a certain extent, we'll ultimately always have to go to the experimental route to confirm our guesses. However, at the moment, we have a big puzzle, which is that the LHC has gone to higher energies and still nothing has shown up. So we've not yet reached that, the scale of the microscopic theory. On its own, that's fine. Of course, there's no problem with that. But the theory puzzle we have is that there is no symmetry that allows the Higgs mass, that macroscopic parameter, to be separated from the scale of the UV completion, which is different from these two examples. The pions are light because there's in the UV, there's an approximate global symmetry at the QCD scale, which is an approximate SU2 left cross SU2 right symmetry. We have spontaneous symmetry breaking when the quarks condense. And that would give us, if it was an exact symmetry, would give us massless pions. And the fact that there's just a tiny parameter, which is the quark masses, which breaks that symmetry, means that they have a small mass. But that allows a scale separation. There's something qualitatively different, but in some senses similar, that happens for the Landau-Ginzburg scalar field, but that's to do with operator dimensions. Whereas with the Higgs, we can't identify in the standard model any symmetry that would protect Higgs and allow it to be separated from the scale of UV completion. So it's natural to ask, what could be going on? I think probably the most natural question to ask is, could the Higgs be like a pion? Could it be a pseudo-Nambu-Goldstone boson? Now, that is a question that's been asked many, many times. The first time it was really robustly asked was in 1984 by these authors, but of course, there's been an awful lot of work since trying to address the question. If the Higgs is a PNGB, and if the UV completion doesn't have some funny features, if it's not fine-tuned, then all of the properties of the IR parameters, such as the VEV of the Higgs, the analogy with pions here, the pion decay constant, the mass of the Higgs, the analogy with pions would be the pion mass, then they have to be radiatively stable against corrections at all scales. So when we calculate within whatever this theory is, we calculate the IR scalar potential, then that IR scalar potential shouldn't depend sensitively on which contributions we're including, if it's contributions from above the cutoff or RG contributions from below the cutoff. Then the parameters such as the VEV, which is the position of the minimum, or the mass squared, shouldn't require a cancellation from physics at these scales and these scales. If it did, that would be a fine-tuning in the context of a quantum field theory. That would be a fine-tuning. If the Higgs mass squared is small, it's 125 GeV, yet you get contributions from the UV, which are a TeV, and then contributions from the matching scale, the threshold, that are a TeV that cancel to give you that small number, then that's a fine-tuning. Otherwise, it should be stable. If it's not fine-tuned, then none of the contributions from any scales should be much bigger than 125 GeV. And similarly, none of the contributions should shift the position of the VEV, of the minimum, the global minimum, significantly. And that's just the notion of radiative stability. That's my way of phrasing radiative stability in this context. But radiative stability is, of course, a much broader concept.
Can I ask a question? Yeah.
Yes, please.
Yeah. So the original idea in '84 was not very welcome because the Tabuga coupling that we measure is order 1, meaning that the essential property of Goldstone boson is derivative coupling, and all the other couplings should be tiny enough to keep those PNGB properties. But the apparent Higgs coupling to the top was not, and so you have an answer to that, or?
The same answer as every other PNGB answer, which is partial compositeness. It is
meaning
possible
that partial compositeness, meaning that you are just borrowing a part of it to be composite and part of it to be Goldstone bosons.
No, so partial composite. So the Higgs would be entirely composite, but partial compositeness has, for instance, in some examples, the top right is a composite operator, and that lets
you accept those modification of top sectors.
Yes, exactly.
Okay, thank you.
So that's the usual trick for getting an order one.
It's also kind of a big assumption, or I mean, you should swallow those big things.
Well, partial compositeness isn't such a big thing to swallow, I don't think.
No. Those compositeness for top sectors. So it's not just about the scalar, but you should also accept those modification of those fermion sectors.
Yeah, absolutely.
Thanks. Yeah.
No, absolutely. I mean, if the Higgs is composite, if the Higgs is like a pion, then that's what it's telling us. Absolutely. But this is not a peculiar thing. You know, if you look at the pion couplings to the rho is a composite state at close to the cutoff. And
it's already at the cutoff, so
yes. But it does, so because the rho doesn't have chiral symmetry, but you can have composite states in the IR theory that, like the tops, which could be light and still have largest coupling to the Higgs. So partial compositeness is its own story, right? There's about a
It's kind of disconnected. It's
oh. Did I do something wrong, or
you pressed wrong button or something?
Okay, no. So yes. So as I was saying, to Hyungdo's question, yes, for the top sector, one would have to have partial compositeness, but I don't really see that as a concern. I should also stake out my territory quite clearly before we go on. One aspect of this process of making guesses from the IR about the UV, like we had with QCD and pions. In amongst those guesses, one element that's often injected is some notion of minimality, that somehow the UV should have not many particles, not many structures. And for me, I should make clear that for me, I think this is a big red herring. If we look at nature, Occam's razor is a very good guide, which says that probably the simplest explanation is the right one. But Occam's razor is not minimality, and nature has told us very clearly that it has no preference for minimality. The standard model has loads of particles and couplings, and it's complicated. And so for me, minimality plays no starring role here. It's not something that I think is a good guide. So necessarily. So for me, partial compositeness in the top sector is fine. Although I'm not going to have anything more, our structure has nothing to say about it. We just take exactly what's in the literature, essentially. Okie doke. So how does this work then for, so as I said, not all PNGB potentials are created equal. Only certain classes will be radiatively stable. You can't just take a PNGB and write down any scalar potential that you want. Only certain types of them will actually be radiatively stable, but using effective field theory, we can actually find out what those classes are. So the first example I have is a very, very familiar one, which is just spontaneous symmetry breaking, spontaneous breaking of a global U1 symmetry. So everyone knows this Higgs-like potential. So this is not a gauge symmetry, a global symmetry. This is a complex scalar, and it's just a U1, so you can multiply the scalar phi by a complex phase. And this is the scalar potential. We know this scalar potential, it's Mexican hat, and phi here gets a vev of f over square root 2. And in the IR theory, because this was an exact global symmetry, we get an exact massless scalar particle, thanks to Goldstones theorem, which corresponds to running around the bottom of that Mexican hat. However, if we have some source of explicit symmetry breaking, this could be explicit symmetry breaking, just like the explicit symmetry breaking that the quark masses do for generating the pion mass, or also the electromagnetic gauge coupling and generating the pion neutral uncharged pion mass splitting. If in the UV theory we have some source of explicit symmetry breaking with some, which is like, we call it a spurion, which is a parameter that we sort of treat like a field. And if we treat it like a field, we can see where it will enter in the UV theory and in the IR theory. So if this spurion has charge Q, then the explicit symmetry breaking operator in the UV will look like this, and in the IR it looks like this. But we can see here that this structure is radiatively stable. At order epsilon, the only thing you can write down is phi to the Q because of the selection rules. If you want to go to phi to any other power, like phi to the 2q, you have to go to order epsilon squared. So if epsilon is small, then those terms will be subleading. And so this scalar potential here is radiatively stable just as a result of symmetries. And what are the properties of this scalar potential? Well, the first thing is that you can naturally have a small VEV. F was the spontaneous symmetry breaking scale, and the VEV of the pion, the Goldstone boson, can be of order f pi times n over q, where n can, if q is a large number, n can be any integer smaller than q. So say q was 10, then you've got a scale separation of a factor of 10. And that is radiatively stable. There's no naturalness problem with that. This pion has a small VEV completely naturally. The mass can also be small because epsilon, if epsilon is a small parameter, you can get a scale separation between the cutoff, which I'm calling m rho here, and the pion mass. Furthermore, the quartic scales relative to the mass with an extra power of q squared. So if q is large, you can get a big quartic. So if you just have a single PNGB on its own, so it corresponds to U1, there's no naturalness problem with having a small VEV, a small mass, and a large quartic. That's something we all know. Sometimes people claim that there's a problem with having a quartic, and I've never understood those claims because it's very clear that this is a radiatively stable structure. So we've all known about this class for a long time. What happens when you consider non-abelian Goldstone bosons? So this is our first paper. Essentially, we studied this in detail, and for some bizarre reason, it was not studied in the literature. This U1 example that everyone learns as a graduate student is very well established, but actually the non-abelian story had not been studied for some reason. So let's go to the non-abelian story. So imagine we have a global SON symmetry. I'm calling it SON plus 1 because I will break to SON, and I'd rather just a choice of convention. So we've got a global SON plus 1 symmetry. Got the usual Mexican hat potential here. These guys get a VEV of f over square root 2. And we have spontaneous symmetry breaking to SONs. We get n massless PNGBs with a decay constant f and the remaining unbroken SON. Then we can ask the question, okay, what if we have some explicit symmetry breaking just in exactly the analogous way as the pions or that U1 example that I gave? So now we have some explicit symmetry breaking spurion, but that spurion, just like with the U1 case and also with the pion mass, the quark masses, is in some representation of the symmetry. So it turns out that well, we can see this from many different ways, but let's take as a guess that the spurion is in the symmetric irrep, so irreducible representation with n indices. Then the explicit breaking operator would look like this, and you can see that if it's in the symmetric irrep with n indices, with n indices, you can see that this is radiatively stable for the following reasons. So if epsilon is a small parameter, this tensor is small, then it turns out that this is the only thing you can write down at order epsilon. There's nothing else exists. So why is that? The reason is that it's an irrep, and because it's an irrep, you can't build smaller irreps out of it. So for instance, if you took, we've got n entries of phi here. Suppose we wanted to have n minus 2 entries of phi. The only way to do that in a symmetric way, in a way that's consistent with the global symmetries, would be to take a trace over 2 of these indices. But if you take a trace, that vanishes because this is an irrep. It's by definition, it's a traceless tensor. That's also equivalent, imagine you in the UV theory, you close a loop of phi's. So you look at a one loop correction here, you close a loop, but if you close a loop, that corresponds, you've joined up two phi's, that also corresponds to a trace. So you get a trace over any of these two indices, but that trace vanishes because it's an irrep. So you can see already by symmetries in a manner that's completely analogous to, well, not completely, but largely analogous to the U1 case, that this, the effective potential you generate from a spurion in the symmetric irrep is radiatively stable. It's radiatively stable because there's literally nothing else you can write down at order epsilon. Anything else vanishes. Of course, you do get contributions at order epsilon squared. That breaks down just like it did for the U1 case. Okay, so then the question to answer is to ask is, well, what is the form of the scalar potential? So writing the usual CCWZ formalism for the Goldstones for the IR fields, we can break our fundamental of SON plus 1 up into the nonlinear representations. This parameterizes all of the Goldstone fields. And when we plug that in to this potential here, we find that the potential is epsilon is still just a small parameter, but it's no longer a tensor. It's just sort of parameterizing the size of it. We find that the effective potential which is generated is a Gegenbauer polynomial, and for reasons I'll explain in a few slides why that is. So from a symmetry perspective alone, you can see that the non-abelian analogy to the abelian case, where the abelian case you had cosine of Q times the Goldstone, here you have Gegenbauer polynomials, and indeed if n was 1, so it's SO2 to SO2 spontaneous breaking to nothing, which is U1, then indeed these Gegenbauers just become cosine of n pi over f. So it's the same thing. This is just a generalization of that story. How can we see this connection? Why do we get a Gegenbauer from this thing here? It's actually, so you actually already know this stuff. When you do the spin decomposition, when you do an angular momentum decomposition, you get Legendre polynomials. Legendre polynomials are Gegenbauer polynomials. So Gegenbauer is just the n-dimensional generalization. So normally for Legendre, you're working in 3 dimensions and you're doing the angular momentum decomposition or spin decomposition in 3+1, things like this. That's what shows up for the same reasons here, but Gegenbauer is just now n is now just any number and any integer, so the n equals 8 if we wanted, or something like that. So you already know this from the angular momentum decomposition, and you probably also remember that you can get the angular momentum decomposition into Legendre polynomials from expanding the modulus of a combination of functions like this. So I'll explain what this is. So phi tilde here, we can think of it as living in the fundamental, but it's the thing that will break the symmetry. So it's a fundamental. So if you break it to SON plus 1 to SON, it's like 0, 0, 0, 0, 0, 1. This phi here is our fundamental representation. And t is just some parameter. So we're going to do a Taylor expansion in t. And it turns out that by definition, this Taylor expansion is in powers of phi coupled to some, the nth term is n powers of phi coupled to some tensor. But you can see that that tensor is symmetric because you just get it from differentiating this. We're doing a Taylor, so we're differentiating. So this tensor k is just the nth derivative of this function with phi fixed to phi tilde, just by the definition of the Taylor expansion. You can see that it's symmetric because derivatives commute. So if I swap any 2 indices here, I get the same tensor. So it's by definition symmetric. And you can also see that it's traceless because if I take a trace that corresponds to, I1 is equal to I2, so this is d of all of this thing by d phi squared, and that's the Laplacian. And I can commute that the whole way through to hit this object here, which is phi to the 1 minus n. And the Laplacian, the nth dimensional or n plus 1th dimension Laplacian acting on phi to the 1 minus n vanishes. Also, essentially by definition, that's how we get delta functions and things like this in potentials. On the other hand, if I take phi tilde to be 0,000,001, then I can just plug that in. So what is this function in terms of that nonlinear representation here? You just plug it in and you see that this function here is just the square root of 1 minus 2t cosine pi over f plus t squared. But at the same time, the generating function for Gegenbauer polynomials is the Taylor expansion of this function here. So you see this function here is just this function here. So that gives you this one-to-one connection between spurions that are in this fully symmetric irrep and Gegenbauer polynomials. It's really just a three-line. It's not a trivial three-line calculation, but nonetheless, it is just a three-line calculation. So that's where they're coming from. That's where Gegenbauers are coming from. It's a one-to-one mapping, and it's sort of not surprising, right? When we do like a spin decomposition in the CFT or even just in a quantum field theory, where the spins, the higher spin operators, are just the irreps under rotations. And we get in CFTs, we see Gegenbauer polynomials all the time because we're actually working in terms of space-time momenta. But those higher spin representations are just the irreps, and then we get those higher spin operators, sorry, are just the irreps under some space-time symmetries. And we see Gegenbauer polynomials showing up all the time when we're talking about scattering fields in a CFT, for instance, for exactly the same reason. So the only difference here is normally they're a function of the space-time coordinates, whereas here it's not a space-time symmetry. It's an internal SOM plus 1 symmetry, and so they're showing up as functions of the Goldstone fields, not functions of the momenta. Yeah, I should speed up a bit. Another way that's sort of, I think, much less powerful and less interesting to see that this structure is radiatively stable. We already know it from the previous arguments, which are just from symmetry, which make it very clear. But another way to see it is that you can actually take a scalar particle with some unknown function g. And
I have one question before you move.
Yes, please.
So for this non-abelian symmetry, so are you thinking of a global symmetry? I mean,
Yes.
First of all, are you trying to apply this phi to be Higgs, or is it really
Yes.
independent? Yeah. Then for the Higgs, you apply some global symmetry under which Higgs is charged.
Yes.
And then also the fermion is charged under that global symmetry.
Yes, exactly. The fermion operators. Yeah.
Okay. Thanks.
Absolutely. So another way to see that it's radiatively stable is to just if we take any potential, and we don't know what it is yet, we just say it's a function of cosine pi over f, and then calculate the one loop corrections. So to do this for PNGBs, you have to include all of the kinetic term structure. So there's the kinetic term self-interactions for PNGBs. So there's this whole, geometry of the metric sort of stuff that you use. And you calculate the one loop corrections to the scalar potential, and you see that they depend on the cutoff like this. But if G happened to be a Gegenbauer polynomial, then we know that Gegenbauer polynomials satisfy this equation here. So G double prime plus 2 lambda cotangent blah 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 G prime is proportional to G, to itself. So it's like an eigenvalue equation here. This is an eigenfunction of this differential operator. And you see that this thing here is exactly the same thing as this thing here. So if G had been a Gegenbauer polynomial, then this quadratic correction is proportional to itself, which means that the scalar potential gets renormalized multiplicatively from the UV, from threshold corrections, things like that, but it doesn't change the shape of the potential. So the minimum will stay in the same place. Furthermore, of course, the corrections are proportional to the small parameter out the front. So this is a completely separate way of showing, and it's less powerful because it's not all loops. This is just a one loop statement, but this is a completely separate way of showing that this is radiatively stable. Okay, so what do these functions look like? So Gegenbauer polynomials look like this. They have n wiggles, so they're like cosines and sines, but they're higher dimensional generalizations. So they have n wiggles. So here there's 20. There's a minimum at approximately 5.1 divided by n, and that's the global minimum. So it's here. And in the middle, the function looks approximately periodic, sort of like a cosine style thing. Okay. So the mini summary then is that for non-abelian Goldstone bosons, it's technically natural to have a VEV, which is naturally small compared to the symmetry breaking scale. So it goes like 5F over N, which is analogous with the U1 story. It's also natural to have a small mass, because if epsilon is a small number, if the symmetry breaking is small, like for the quark masses and pions, then the mass can be naturally small. You can have a scale separation. There's no problem with that. And furthermore, the quartic has an extra 2 powers of n. So if n is a largish integer, you can have large quartics as well. So just like with the abelian case, there's actually no naturalness problem with a PNGB of having, even if it's non-abelian, for having a small VEV, small mass, and also large quartic. Okay, so now let's apply this to the Higgs. So we're just going to use the same old minimal composite Higgs model that has been studied to death in the literature. I don't know how many papers there are on it, but it is something like 1,000, or at least mentioning it somewhere. So we'll consider SO5 spontaneously broken to SO4. We'll have the usual kinetic terms, which are symmetric with respect to the global symmetry, except for the gauging of the electron subgroup. So they're now become covariant derivatives. This is a well-known story, so I'll not go through all the details, but from the covariant derivatives alone, you see that the Higgs couplings to vector bosons are modified relative to the standard model by this factor here, where F is the symmetry breaking scale and V is the electroweak scale, which is the VEV of the PNGBs. So you get a direct connection between the VEV and coupling modifications. And that's essentially why the composite Higgs models are under a lot of tension now, because Higgs couplings look to be sort of standard model-like at order 5% or so. And so that this means that V squared over F squared has to be a pretty small number. It has to be about 10%, 0.1.
Can I ask a question?
Yes, please.
Regarding the UV potential that you started with. In the on a U1 abelian case, abelian Goldstone boson, you broke abelian U1 symmetry to discrete Gn something, right? In the case of non-abelian Goldstones, are you also breaking it to some higher order discrete symmetry somehow?
This is the question. We don't know. So we've been studying this a lot, because that would give a further explanation for what's going on. Exactly, because like you're saying, in the U1 case, we have a Zn symmetry in the IR. We can see it as a discrete shift symmetry, and that's another way to see that it's radiatively stable and things like this. It doesn't seem to be the case for the non-abelian story. We've not found any remaining non-abelian discrete symmetry in these potentials. And one way to see it is that, even at the level of the potential, there is no symmetry here. If we translate this, unless n is very large, maybe in the middle it sort of looks symmetric under shifts. Out here it doesn't, and so the potential is not showing any signs of a symmetry. But we've studied it to death. Things that don't correspond to symmetries in this way, but may correspond. Have you heard of point group symmetries in crystals and things like this? They have a similar story where you can get a connection between symmetry breaking with a large index rep and the point group symmetries, but they're a different sort of symmetry. So it's something we're studying really hard, and I think it's sort of what you're asking is sort of the leading question to understand the structure a bit better.
But then just you assume that the leading contribution from UV started from this high order Gegenbauer polynomial, and even if you add even higher order Gegenbauer polynomial, it's still fine. I mean, just you are changing a little bit. You are getting more minima in the presence of higher order polynomials, right?
So what it means is, sort of take your statement to modify it slightly. What it means is that in the UV, the only symmetry breaking is in a high index irrep, which is like having a large charge operator for U1. So we're assuming that there's no symmetry breaking, explicit symmetry breaking at lower dimension irreps.
Right.
And so somehow you want to have some narrative where that emerges as an accidental symmetry. You know, you don't want to put it in by hand. You know, in with the U1 case, it's very straightforward to write down a theory where accidentally, because of an interplay of gauge symmetries, you can only have a charge Q operator. And what we're doing at the minute, and I'm not going to discuss this, but what we're doing at the minute is trying to find a way where that could emerge as an accidental symmetry. And we have a way of doing that, but it's not obvious. But these are what you're asking is really our current research program. these in my view, these are the leading questions.
You see, so 1 or 2 papers coming out.
Yes, exactly.
Okay.
Yes. So I haven't answered your question, but I at least you know that I'm taking it seriously, because I can't answer it very well at the minute. Okay, so so we're still talking about just the usual composite Higgs. Now the explicit breaking in the top sector gives correction to because there's some explicit breaking there, essentially because the top is not in a complete multiplet of SO5. So that multiplet has some breaking. There's many ways to do that. But generically, you get a correction to the potential, which looks like this from the top sector, where kappa is some order 1 number that depends on the UV completion. This is much like the way you calculate the neutral and charge pion mass splitting in QCD. You have some unknown UV contribution, you know it's order 1, then you can estimate the scaling of the rest of it. But you see, if this is your only scalar potential, then the VEV is typically at 0 or pi f, nowhere in between. That's because of this function you get. And this property also typically persists even when the gauge loops are included, and also that typically the Higgs mass is too big as well. So what one normally does is then starts fine-tuning parameters so that you can balance this against some higher order correction, and then you can shift the VEV to be not 0 or pi over pi, not 0 or f, but somewhere in between. And you have to tune by an amount that's v squared over f squared typically. So what we said is, well, what if it's very analogous to the pion sector? So there's some explicit breaking from interactions in the IR, which is the top sector, and that's like the explicit breaking from QED with pions, and then some additional source of explicit symmetry breaking, which is completely unrelated, like the fact that the quark masses are not related to the QED gauge coupling, completely unrelated. But what if that is in a higher index irrep? And the full scalar potential in the IR would look like this. There's the usual top contribution and a Gegenbauer contribution. We've just absorbed these constants into a definition of the coefficient here of the Gegenbauer bit. So that's a free parameter gamma. And so if we have these 2 contributions, then what happens? And what happens is very interesting, because this contribution can be big, but the derivatives of this contribution, because it wiggles faster, can be big. So it's sort of a little bit like the relaxion. Even if the size of this term is smaller than this term everywhere, the derivative picks up an extra power of n. The derivative of this term can be bigger than the derivative of this term. And what that can do is that it can force a global minimum to appear when you combine with the usual scalar potential. So this is what it looks like. So as gamma becomes as gamma becomes big, so gamma c over gamma becomes small, then the potential becomes more and more Gegenbauer-like. As gamma becomes small, gamma c over gamma becomes big, so it becomes more and more like this. And at a critical value of gamma that you can actually calculate for a given Gegenbauer polynomial, the potential moves back exactly to 0. So there's some gamma can be too small. There's a size of gamma which is so small that the minimum of the potential is at the origin. Okay, so this is what the potential looks like for different values of gamma. We have no idea what gamma is. what it should be, just like we've no idea what the quark masses should be. That's a question for flavor physics and understanding why the UCAWs are what they are. But this is what the potential looks like for various values of gamma. So we can take this potential and calculate the fine tuning. There's two sources of fine tuning. There's kappa. We might need kappa to be small to get the Higgs mass to be small. And we might need to tune gamma to get the VEV at the right place. So those are the two, there's two independent sources of tuning, and we take the product of them. They both scale in this way. That's not so important. I need to start hurrying up a bit. But when you take these two sources together, what one finds is that this can radically reduce the fine tuning. The way it reduces the fine tuning is it doesn't change the tuning for the top sector at all. What it does do is it can naturally make V over F small, because these Gegenbauer polynomials naturally have V over F small. N is just some integer. It's not a fine-tuned parameter. And so you naturally get resolve the V over F tuning, but you don't resolve the top sector tuning. So we find that there's regions of parameter space. So here in solid is the tuning in gamma, and that dot dash is the tuning in kappa, which is like top sector tuning. And taking the product of them, we see that there are sweet spots, around here, where F can be really quite big and V over F can actually be small. So if we take n equals 10, so this is quite a large irrep, then there are regions of parameter space that are less than 10% tuned, but are completely consistent with all LHC measurements. So this is a very natural theory with a standard model like Higgs, contrary to usual composite Higgs models. Okay, phenomenologically what happens? For this benchmark that we chose, because F is so big, here F is 2 TeV, then V over F is very small. So the Higgs coupling corrections to vectors, for instance, are very small, but a modification of the Higgs self-coupling can be quite big. Here, it was less than 10%, but 10% is a lot bigger than 1%, which is the other coupling modifications. But for the higher index irreps, you can have much bigger corrections of the Higgs self-coupling. And as I said, explained before, sorry, this is natural. There's no fine-tuning required to get a big modification of the Higgs self-coupling. Okay, so I've only got like 7 minutes left, so I will speed up a bit for the twin section. But just to summarize briefly, the main points so far were that any PNGB potential can be decomposed into a sum of Gegenbauer polynomials. This is just like doing the angular momentum expansion. It's really the same thing. Or equivalently, a sum over higher dimension spurion irreps. Again, it's a one-to-one mapping between the two things. Two ways of stating the same fact. If you have a single Gegenbauer polynomial that dominates, or even if there's just exactly one of them, or if only one of them is the biggest, then that scalar potential is radiatively stable against unknown UV contributions and against contributions at the matching scale, for instance, threshold corrections, things like that. And one can naturally have a parametrically small mass and VEV for PNGBs of SON, spontaneously broken SON, even if there are large self-interactions. Okay, this I just said very recently, so I will go ahead. Okay, so the second paper was based on a very simple observation, which is that this Gegenbauer story has a way of alleviating V over F tuning. But as you saw, it didn't do anything for top sector tuning. As far as composite Higgs is concerned, top sector tuning was completely unchanged. On the other hand, we know that twin Higgs models, they can't do anything about V over F tuning, but what they can do is alleviate top sector tuning. And so the natural question to ask is, if we combine the two, can we sort of hit both in a game of whack-a-mole, hit the V over F tuning and the top sector tuning at the same time? And the answer is yes. So how do twin Higgs models work? This is Gegenbauer, by the way. So twin Higgs models, I'll just do a rapid recap here. In twin Higgs models, you have, at least in the initial incarnation, two copies of the standard model. Everything's twinned. The only interaction between the two sectors is through a quartic interaction like this. And one assumes that the quartic interaction accidentally respects an SO8 symmetry. The only way to really get that accidentally that I know of is in a SUSY scenario, but there are other ways to motivate it. So if the quartic interaction accidentally has this form here, so that the cross term is related to the individual quartic terms squared from this square in a way that sort of accidentally respects SO8 symmetry, then what you have is, because this is a complex doublet squared, so you've got four fields squared here, 4 fields squared here, you see that automatically, just if you have an exchange symmetry, the mass terms, if they're exchange symmetric, will respect that SO8 symmetry, global symmetry, and UV corrections that scale like, you know, masses of order the threshold corrections or the cutoff will also respect it accidentally, just because you've got an exchange symmetry. And so what this then looks like in effect is just another PNGB Higgs model, but it's of a particular structure. So you have SO8 spontaneously broken to SO7, but because the both sectors were twinned, you've gauged this electroweak subgroups. And so 3 of the Goldstones are eaten to become the longitudinal modes of the twin sector W's and Z's. And that means you get 4 left over, and those 4 are just the standard model Higgs. And so this is a very neat structure. One can, of course, in a sort of very outdated way, look at the quadratic divergences, and you see that they all cancel, but they're all canceling essentially because this one reason here, which is that if you have an exchange symmetry, then the mass corrections will always respect an SO8 symmetry by accident. So you see that the quadratic corrections all cancel. This continues to higher loops and so on. And the only connection between the two sectors is through the Higgs portal. However, there's still the twin tuning problem, because if there's an exact exchange symmetry, then you see that you either want to have a vacuum which will be the same VEVs in the twin sector and the standard model sector, or the vanishing VEV in the standard model sector and a VEV of order the spontaneous symmetry breaking scale in the twin sector. Either would in principle be fine, but we know electroweak symmetry is spontaneously broken, so you'd probably opt for this one. But the Higgs coupling modifications are the same as in the standard composite Higgs, so they scale like square root of 1 minus V standard model squared over F squared. And so this would be order 1, and so we would get huge Higgs coupling corrections, which we've not observed at the LHC. So the only way then to change this is to include some extra explicit symmetry breaking, and then when you calculate the fine tuning, you can actually show that reducibly that leads to a fine tuning of order 2V squared over F squared. And so this is the similar to the fine tuning of V squared over F squared fine tuning of the composite Higgs, but there's an extra factor of 2 because of the twinning actually. Okay, so one can calculate the top sector contributions to the IR potential in the usual way, just the way you do for the usual composite Higgs, except the group structure is slightly different here. And this is what you get from the top sector. You can see it's exchange symmetric. A is just some unknown number related to the UV cutoff. So it might be the mass of fields at the threshold corrections. And that's the only parameter you have to play with here, because symmetry fixes the prefactor. If we include on top of that then an additional source of explicit symmetry breaking in the n-index IREP, then you would get, in addition to the top sector potential, you would get a Gegenbauer polynomial, which we can calculate. Again, the group theory structure is slightly different. You get an extra factor of 2 here, which shows up. And so our model would have then, if we did Gegenbauer's twin, would have 2 parameters. This unknown parameter, which is in the usual twin setup, and now the new parameter, which is just some small number, I'm calling it at bar. Now I guess n is a parameter. You could, in principle, UV complete this in strongly coupled or SUSY scenarios. So when we calculate the fine tuning in this setup, we find something very interesting. So in black here is the usual fine tuning relative to this sort of benchmark fine tuning of 2v squared over f squared, and this is delta is the total fine tuning. So we're taking the full fine tuning here, including all sources. For the usual twin models, often the explicit breaking that's introduced is by not gauging twin hypercharge, but there are many other ways of doing it. They all have fine tuning of order 2v squared over f squared, and we see that here. So we've calculated it, you know, completely, and we get that. It's not exactly 2v squared over f squared, but it's pretty close. You see, this is almost 1. But when we add the Gegenbauer polynomial, what that does is it naturally, the derivatives can beat the derivatives of the top sector contribution and introduce a global minimum at small v, and that's technically natural. And so that we see the tuning improves dramatically. It's a sort of a factor of 4 or so. If we have a 6 index irrep, for instance, we get about a factor of 4 here. And it turns out that, and this is how we calculated the tuning. We calculate the full sort of matrix of derivatives, and then take the eigenvalues and take the biggest eigenvalue, which corresponds to the biggest tuning throughout. It turns out you can actually make it look even more natural if you just do the usual story, which is take the biggest entry here, but there's a conspiracy. And so for certain regions of parameter space, the fine tuning is more than the usual measure of tuning would give you when you just take the biggest one. And so, because there's correlations between the parameter changes, and so you really have to take into account those correlations. So this is the most conservative definition of tuning that we could use. It maximizes the amount of fine tuning in some sense. Plotting it now, not relative to 2v squared over f squared, but just the fine tuning on its own, you can see that this is the usual twin model, and you can see that for f of order, you know, 1 TV or smaller f here, when f is of order 0.1, which is what you need. Sorry, v squared over f squared is 0.1, which is what you need to be consistent with LHC measurements. The fine tuning is of order, I don't know what this is, 60% or something, just not fine tuned. Whereas the twin Higgs is already tuned at, you know, the 20% level. But furthermore, we can go to larger f, where v squared over f squared is becoming smaller, for instance with Higgs coupling modifications at the percent level, and still the fine tuning is, you know, of order 30% or something like this. So these are very, very natural theories. I would say that there's essentially, you can be consistent with LHC measurements without any fine tuning in this scenario. What's interesting is that you get really, in this model, you get really big modifications of the Higgs self-coupling. So we've got contours here. Green is the contours of the modifications of the Higgs self-coupling relative to the standard model self-coupling as a function of f. And we've got n, which is the number of indices in this irrep. And in blue, we've plotted contours of fine-tuning. So you see you have models here with 50% fine-tuning, which is essentially not fine-tuned. And, you know, 30% modifications of the Higgs self-coupling. Here you've got, you know, 160% modifications of the Higgs self-couplings. These are really big modifications of the Higgs self-coupling, whereas the Higgs single couplings are still at the, you know, for here, they're still at the few percent level. So this is unlike the usual lore in the literature, which is that in natural models that the Higgs self-coupling modifications are a similar size to the other coupling modifications, which then leads people to say, well, why do we really want to measure the Higgs self-coupling in the first place? Well, here, this completely contradicts those statements. Here, the Higgs self-coupling modification is hierarchically bigger than the other Higgs coupling modifications. So this is a scenario where new physics could actually show up first by measuring the Higgs self-coupling, which is not true for SUSY or standard composite Higgs models or standard twin models or anything like that. Okay, so I'll wrap up now. Sorry, I've gone a little bit over. So to summarize that part, I'd say that Gegenbauer's twin is a symmetry-based model for the Higgs sector, which is at present completely natural. Future signatures include this greatly modified Higgs self-coupling and very standard model like other couplings. And it's, as I said, it's really an explicit counterexample to the usual lore that you won't discover natural new physics first in the Higgs self-coupling. More broadly, you know, I'm guilty and others of declaring a naturalness crisis because traditional symmetry-based approaches to the hierarchy problem appear to be under a lot of pressure from the LHC. Whereas on the contrary, this work suggests that there's really no naturalness crisis, at least for PNGB Higgses. It's really an aesthetics crisis. The element of human aesthetics that's been injected into models, which is essentially an element of minimality, of requiring, for some reason that I still don't understand, requiring that models are minimal, has led to an accepted set of generic predictions that is not really generic for PNGBs. It's just generic for PNGBs where you require that the UV structure is minimal. And so I'd say that there's really an aesthetics crisis as far as PNGB Higgs models go, not a naturalness crisis. And I think, in my view, our perspective on naturalness has been too much influenced by minimality, and not by EFT arguments alone, but by really saying that, well, we require that it's, and I don't mean minimality in terms of group structure. People have studied for PNGB Higgs, there's lots of different cosets, right? I don't mean minimality in that sense. I mean minimality in terms of the sources of explicit symmetry breaking in the UV. You know, usually for the composite Higgs, one assumes that the only sources of explicit breaking are the top sector couplings and the gauge couplings and nothing else. But that's even in contradiction with what the standard model does with pions, right? The standard model has two completely different sources of explicit symmetry breaking, which are the quark masses and the QED gauge coupling. And so I don't see why we inject this minimality thing all the time. It seems to me to be potentially misguided. And so I would argue that technical naturalness appears to be alive and well to me at the moment, but not minimality. The open questions are the questions that Hyunmin already asked, so I don't need to repeat them. But this is our current research program, which is to motivate why this explicit symmetry breaking would be originating dominantly from a higher index irrep, not n equals 1 or 2, which is what we normally would assume. And could that be connected to symmetries? So I'll stop there. And thank you for your time, and sorry for my computer crashing halfway through.
Thank you very much for your nice talk. Now it's time for question and comment. If you have, please go on.
So what's the scale of this top partner, capital MT? Is it the same as F, or?
Yes, it's usually close enough. So for this, so in the twin sector, slightly different because the top partners are neutral, and so the true top partners are at the compositeness scale, which is really the cutoff. For the usual PNGB Higgs MT here, which is the mass scale of those top partners, is of order lambda top times F, so around F. But they can actually be a bit heavier. You see, they can be lifted. So that's the mass that they would get just from the spontaneous symmetry breaking, but they can be lifted also with explicit symmetry breaking. So they can be a bit heavier. So for instance, you know, in these models here, when F was around, this was F at around 2 eTV. The top partners were around 2 eTV. Well, you see that here. So this is all for F for MT was 2 TV, and we can have lower F. You know, here F is 1 TV. So that's implying that there's a source of explicit breaking in the mass of the top partners, which is splitting them. But here, the top partners are mostly getting their mass from lambda top times F.
I think,
but you can't have them.
For your conclusion, I mean, you said that minimality was, too much emphasized, but I think the issue is if you accept this idea, then it's not only about the scalar sector, but also the fermion sector. The top should be a composite, and all those complications arise at the same time, and there should be a kind of early precursor for those indications, but we haven't seen any. And given that signature or the circumstantial evidence of no extra indication in the fermionic sector, I think people are trying to focus on the scalar itself. So always this PNGB idea or the composite Higgs comes with significant modification of the fermion sectors. So you should expect a bunch of another particles at TeV or 2TeV.
Yes.
And we haven't seen any. So you're saying we are misread, but I
right,
think
exactly.
The community is
but,
correct in this sense.
No, so I disagree. So why do I disagree? Because by fine tuning arguments, if you just in the usual PNGB story, the top partners, if you want the theory to be in any way natural, the top partners here have to be, at 700 or 800 GeV.
Mm-hmm.
Because that's the scale of F, and so they should have shown up. I completely agree.
So that's 10% tuning, or I mean, what's your
10% tuning. So 700 or 800 GeV. When you alleviate the V over F tuning, and that's related, you see, to the V over F tuning. When you alleviate the V over F tuning, you only have the top partner tuning, not the V over F. So the total fine tuning can still be at 10%, and your top partners can be at 2 TeV. Now, there's no reason to expect colored partners to have already been seen if they're 2 TeV. That's large for the LHC.
It looks like that's an extra accident, like correction to the pion mass. Both are MEV, but there's no reason from the beginning that those QED correction and the isospin breaking should be comparable, right?
Right, and, but they're not. They're completely different. It's not an accident, right? Here, the scalar potential is completely dominated by the Gegenbauer. It's just bigger. Just like the contribution to the pion potential from the quark masses is just bigger than the QED by an order of magnitude. And so, or more than an order of magnitude. So it's just bigger. It's not an accident. It's just bigger. But the important point here is that minimality made us focus on this potential here before. And that said, the top partners, the fermionic sector, should have new resonances at 700 or 800 GeV, and we didn't see them, and so we're worried about them. What I'm saying is if we relax minimality in terms of the symmetry breaking, then we see that the top partners, these new resonances in the fermionic sector, could be well beyond LHC reach. We shouldn't have seen them yet. So you can't decouple the two questions. That's my argument.
Okay.
And I think it's important to, sorry, go ahead.
So do you want to say something?
Yeah, so I was just going to say, I think it's important. I think that this, because, if you look at the PNG, I have nothing to say about Susie, by the way, here. I don't know, it would be great to have something similar for Susie, but we've tried and we can't figure anything out. But, the PNGB models, this V squared over F squared tuning has always been a result of this assumption here that all the symmetry breaking is dominantly in the top sector, which corresponds to just an n equals 2 irrep. It still corresponds to a Gegenbauer polynomial, but it's just a Gegenbauer polynomial of 2 because it's by assumption in a low dimension irrep. And I think that has really greatly influenced, how we think about fine tuning in these models, where we think the resonances should be not just the top partners, but also the rows, which are an important part. The rows should be of order G star F. And when F needs to be low for fine tuning because of V over F tuning, then also a significant source of tension on composite Higgs models is the fact that we've not seen vector resonances yet. And so I think all of that has really conspired to give a picture of PNGB Higgses that is not very accurate. It's really all of these sort of folk expectations have their roots in minimality, not necessarily in effective field theory. That would be my argument. Even with respect to flavor as well, because there's a big flavor story behind these models. Sorry.
Okay.
All I want to
maybe some students, some other young fellow.
Can I ask one more question?
Sure, please.
You're not young. You're not young.
I mean, when people compute this Coleman-Weinberg correction, they ignore the quadratically sensitive mass corrections and just focus on the quadratic because it's a kind of preliminary assumption that you are taking the mass scale to be 0 from the beginning and keep it to be 0 till the end. But when you discuss this fine tuning, always that quadratically sensitive correction should be taken into account. So I don't quite understand where your expression contains in it, or you did not.
So for the Gegenbauers, do you mean?
Yeah. So is
yeah.
it?
So that's included. So this was the.
So the capital M is the. Oh, I see.
So this is the one loop correction, and this is the quadratic. So it's a bit misleading because the quadratic corrections, you know, in Pauli-Villar's cutoff scheme, they're not physical, but what they do tell us is what the likely corrections are from the threshold and the UV.
Yeah, but you know, then for given the explicit breaking, what's the rationale for not writing down the quadratically sensitive bare term?
So it's here. So, and as I said,
yeah, this is a one correction, right? So I'm asking, what's the rationale for not writing down the three-level bare mass term or whatever, the explicit breaking of those?
So this is the potential from so there's no explicit breaking in the UV, then there's no potential, right? It's just vanishing.
Mm-hmm.
And so this is the explicit breaking here, and that gives us the Gegenbauer polynomial. That's the only thing you can write down.
Okay, and it's really the last question. So this seems to be connected to the paper of Anson Hook, right? Who considered this breaking with a large N or large Q in your notation. But and then I remember that there was a discussion saying that it's kind of breaking of your unitarity, or I mean, you are dealing with a strong coupling regime, and the effective tube coupling is lambda q to the fourth. So I forgot the details, but
yes. So
not as simple as what you described here. No. Can you comment?
So his construction was for an abelian symmetry for a single Goldstone.
Yeah, for abelian. Yeah. And
for me, I mean, there is a problem with. I don't know what problem it solves, right? Because from the perspective of technical naturalness, for an abelian Goldstone, there's no problem with having a large quartic. So I never really understood that paper, because if you have a single Goldstone boson that has just a potential like this, then which just comes from a Zn symmetry, as Hyunmin said, then there's no problem with having a small VEV, small mass, and big self interaction, which seemed to be the problem he was trying to solve in that paper, right? Was the self interact, was to try and explain that you can have a big self interaction, but from a naturalist perspective, there's never been a problem with having a self interaction, as far as I was aware.
Okay, I'm done. Sorry.
Oh, thanks. Thanks, Hyunmin.
Yeah, thank you for your question. Yeah, you can. Yeah. So I forgot my question during the discussion. So please, some of you in the audience, you can ask some question. So Matthew is here. I think it's a good time to ask him. Maybe it could be simple, and it's an elementary question.
Can I ask a simple question?
Yeah, sure.
I wonder the extension of this method to the, for example, general symmetry breaking for the general, for example, Kozetto space. So you determine the explicit breaking potential by comparing the Coleman-Weinberg, right? You require, how to say, kind of a proportionality to between the explicit breaking potential and the Coleman-Weinberg. So this kind of method can be applied for the more general class, or
So I don't know. So it's a great question. It's a really great question. I don't know. So in some sense, so there were two ways of saying this. The one was with the Komen-Weinberg, which was a one loop statement. And the other is with the spurions, which is an all loop statement. And with the spurions, what you would have is, so imagine we did a SUN, for instance, you'd have fundamentals of SUN and some irreps here. We haven't studied it, so there must be an answer, but we don't know what it is, what function you get. The reason we haven't studied it is things get more complicated with SUNs, because then you have like the anti-symmetric tensor. You can form invariants in more ways than you can with SON. So it's not so clear how to do the spurion story. For the Komen-Weinberg part of the story, then indeed one just has the coset structure in the metric, in the kinetic terms, and you should be able to just calculate this and see what the function is. That you'll get some eigenvalue equation like this, and it may be a Gegenbauer, but it may not be a Gegenbauer. We haven't actually done it. We've talked about doing that calculation, but we're trying to answer essentially the questions that Human was asking first. So it's on our list. I think it's a really interesting question. And the answer is, I don't know what the functions are for something like SUN plus 1 to SUN, or also SP groups are interesting. We do know the answer for some cases, because there are cases, I think, like SU4 to SP4 or something, I can't remember, where using an isomorphism, you can see that they're actually SOs on both sides, SO6 and SO5 and things like this. So you can map using isomorphisms. For certain cases, we know that those cosets will give us Gegenbauers, but that's only because on both sides we map to an SON group. But for the general case, we haven't done it, and it's also not in the literature. So this statement here, this one loop statement, was actually in the literature in the 70s when people studied 2D CFTs. They noted that for Goldstones, for the nonlinear sigma model in 2D, that Gegenbauer polynomials are RG invariants for the same reason. So that's the only place I've seen this show up. Gegenbauers show up in physics all over the place, especially when one talks about space-time symmetries and momentum and spin and things like this. But that's the only place I've seen it show up for an internal symmetry, and that was for SON. For SUs, I don't know, but I think it's a really interesting question.
Okay, thank you.
I have just a simple question. I think you have the original Gegenbauer polynomial for SO5, and you twin
Yes.
Gegenbauer. You have a correction to the Higgs trilinear coupling in both cases. So, but do you have any difference between the two cases? In principle, can you distinguish between one Higgs and twin Higgs scenario?
Okay, so to answer, I'll tell you where they come from. So in the twin case, we get a bigger correction because we get this factor of 2 in the argument. So when you differentiate 3 times, you get 2 cubed, essentially. So you get a bigger correction. That 2 came from the fact that the explicit breaking for the twin is SO8, like diagonal to 2 SO4s. Whereas in the other case, we had SO5 to SO4.
Yes.
And that was the, but if we didn't discover the UV fields, if we just have the Higgs self-coupling corrections, if we measured them, imagine we can measure them precisely, and the Higgs ZZ coupling corrections, for instance, then I don't think you could tell them apart, because there's always a free parameter, which is n, the index of the error rep. So I think you would need to measure the self-coupling and the Cortical coupling to break that degeneracy. With that IR measurements.
I see. Okay.
I think.
Okay. That. Okay. That's good. Yeah. Yeah, it's really nice to generalize it. Yeah, this idea. Oh, okay. Sorry.
So you show about the trilinear Higgs coupling, but how about the quartic self-coupling?
So yeah, so great question. Good to see you, by the way, Donald. So there, the Cortic corrections are even bigger. The Cortic corrections are gigantic. We did plot it. I don't know if it's in the paper, but we did plot it out, and they get another factor of 2 relative to the standard model. So those corrections are gigantic. We didn't. It's much harder to measure the Cortic though. So when we estimated, because there are people have done the LHC studies for measuring the Cortic and what scale you can get access to. And when we compared to those, it's a balance between the size of the correction and the experimental story. And so when we compared to those, the cubic coupling is the most promising for discovery, where the correction is big and you can see it. The Cortic corrections are much bigger, but it's also much harder to measure it at the LHC or colliders. So the discovery opportunities are more significant in the cubic, but the Cortic does have gigantic, generically it has gigantic corrections. They're really big, and they can also flip sign, things like this.
So any other question or comment?
Yeah, I have one simple question, I think.
Yeah.
In the Gegenbauer potential, you have many minima. So in principle, I could think about tunneling. And is there any way to avoid appearance of domain walls?
This is a great question. We worried about this a lot. Where is it? Right. So so indeed, so there are 2 aspects. So this could significantly modify the story for the electroweak phase transition if you reheated to above this scale, because you could momentarily settle into one of these minima and then you tunnel across. We calculated the tunneling time, and it's short, so it's not like we could live in this minima, but indeed that could lead to signatures like gravitational waves and things like this, and it could significantly modify the electric phase transition. In this example, there should be some sort of quasi-topological defects associated with tunneling from here to here, but as you can see, there's no Zn potential, so we don't really get domain walls. There's an it looks in this region like it's approximately Zn symmetric, so we would get domain walls, but they would be unstable because it's not an exact symmetry, and we estimated that they shouldn't be a problem. However, in the twin sector, there is a further symmetry. I didn't plot it here, but the potential, the Gegenbauer potential, does have an additional symmetry which corresponds to exchanging the Higgs for the twin Higgs. It's like a Z2, and we do have a domain wall problem with that. So there has to be some other source of explicit breaking that it can be quite small, but that breaks that. It's like an exchange symmetry, a Z2 exchange symmetry, and so that one does have domain walls. So we have to have some additional ingredient there. Either we have to have a cosmological ingredient where we reheat to below the phase transition, so we never go through that phase transition, we never create the domain walls, and any work that were created before are inflated away. Or we could have a field theory solution where we do reheat higher, but there's some explicit breaking, additional source of explicit breaking that makes those domain walls unstable. But yeah, it's a great question.
Thank you. It's interesting.
Yeah, interesting.
So, any other question or comment? So, if not, let's thank speaker again. Thank you very much.
Thanks
Thank
very
you,
much.
Matthew, and Hyungdo, also other people.
Yes,
I
thanks
mean,
everyone for the fantastic.
I have something to ask you. Actually, I became a new representative of Korea Sun theory project in Korea, and then I sent an email to Bruce Wiedemann